Hi, well, we will solve the example number 2 of section 12.5. So we have a particle that travels along a path that is y equals 0.5 x squared. And we know that the position when t is equals 0 is x equals 0, y equals 0, and c equals 0. So we can actually draw our coordinate system, right? And we know that for t equals 0, all position x and y are 0, and c that comes out of the blackboard or the whiteboard is 0 as well. So we have a path, right? So we can draw it like that, and we know because we know that it's a parabola. So our particle is somewhere about here. If we want to find the position, velocity, and acceleration of the particle for t equals 1 second. So we can start by the x components. We know that our velocity, which is x dot, is equals 5t in feet over seconds. We know that the velocity is the derivative of the position. So we can write the derivative of the position is v dt. We integrate both sides of the equation for s equals 0 s and t equals 0 t. And we have that the position, the final position that we want to find, is the initial position that we already know that is equals 0, right? For times 0 plus the integral of the velocity in x direction. Let's do that specific for x will be 5t dt between 0 and that time that we want to calculate. That will be 5 times square over 2 evaluated in t equals 1 second. So that gives us that our position x will be 2.5 feet for t equals 1 second. To find the acceleration, we know we have to derive our velocity. So that our acceleration will be the derivative of our velocity. That will be the derivative with respect to time of 5t, which is very easy, is 5. So we know that our acceleration in x, which is equivalent to x 2 dots, will be 5 feet over second square. Let's find out our y components. We have the expression of y respect to x. So we know that our velocity respect to y, which will be y dot, will be the derivative respect to time of the expression 0.5 x squared. So we have 0.5 is a constant, and then we have 2x, and then we have to derive our x respect to time, which is x dot. And actually we have the position is 2.5, and we have the velocity that is given is 5. 4 times equal. So we actually can evaluate this expression and say that y dot will be 0.5 times 2.5 times x dot evaluated for. So we can say here that our velocity for t equals 1 second is equals 5 feet over second, right? So we have the position, the velocity, and the acceleration in x component. So here we have 0.5 for 2 times 2.5 times 5. So finally, we get that our velocity is equals to 12.5 feet over second. So the position is easy because it's given, but at the end we want all the values, right? So the position is y equals 0.5 x squared for t equals 1 second. We know that x is equals to 2.5 feet. Therefore, y will be equals to 0.5 times 2.5 squared. So that gives us the position will be 3.125 feet. And we need only the acceleration. So y2 dots will be the second derivative of y or the first derivative of y dot. So we have to derive this expression twice. So we have, this is 1 times x dot plus x times the derivative of the second. Then I have, if I evaluate those values here, I have the x dot, which is given is 5 squared plus the position, which is 2.5 times the acceleration, which is 5, give me then my acceleration in y component, which is equals to 37.5 feet over second square. So we have our three values for the position, velocity, and acceleration in x component, the position, the velocity, and the acceleration in y component. Let me find the magnitudes. So for the position, we would call r will be square root of x squared plus y squared, which is equals to square root of x squared and y squared will be 2.5 squared plus 3.125 squared. That gives me equals to 4 feet. I do exactly the same for the velocity. Will be the square root of x dot squared plus y dot squared, and I have the values right here. And if I square those two values, I get the 5 squared plus 12.5 squared, which is equals to 13.5. Very important, the units, don't forget the units, feet over second. And the acceleration will be the square root of x2 dots plus y2 dots, each one to the square. I'm not going to write the numbers, but it's 5 squared plus 37.5 squared, which gives me the value of 37.8 feet over second square. So those three values represent the magnitude. This is the magnitude of r, this is the magnitude of the velocity, and this is the magnitude of the acceleration.